Okay, there you go. Yep, so what I'm going to do today is to continue on with the last part of neutrinos in homogeneous cosmology. And then in the second half, I will start talking to tell you about the theory of inhomogeneities. Okay, and the last two topics here will be the content of tomorrow's lecture. Okay, so let's go. Now, so last lecture I told you about how we predict that the theory predicts that there is a cosmic neutrino background. And then we had some discussion about the detectability of this background. And as after the lecture, and as you probably have gathered now, we cannot really detect the C nu B in the lab at the moment. People thought a lot about it, but it's not something that can be done right now because the neutrinos are weakly interacting and the C nu B is very, very low in energy. However, having said that, because the C nu B was produced 1 second after the Big Bang, and there were a lot of events that took place throughout the history of the universe after the formation of this background, what this means is that it's still possible to discern the presence of this C nu B from its impact on those events that took place after its formation. So primarily we're talking about events like nucleosynthesis, which tells us, which is a theory that gives us the primordial light element abundances. The CMB, of course, we have all seen, and a large-scale structure distribution. And all of these different probes can be are sensitive primarily to different aspects of the C nu B. Okay, so today I'll tell you about how the light elements and the CMB anisotropies are sensitive to this N-effective parameter, which I'll define in a bit. At least I'll do that in part 1. And in part 2 of this lecture series, I'll tell you about how neutrino masses and interactions can impact on the CMB and the large-scale structure distribution. Okay, so now to begin with, remember that we saw these two pies that tells you about the energy distribution in the universe. And in particular, if you look at the pie over here on the right-hand side, that's the energy distribution at the time of photon decoupling. So that's 13.4 billion years ago. And what you see immediately is that you have 10% neutrinos and 15% photons. This is not by accident. This is actually, this distribution of photons to neutrino energy density, which goes something like 0.68 if you have 3 families of neutrinos, is actually a standard model prediction. Now, how is it a standard model prediction? Well, recall that in the standard hot Big Bang picture, the C nu B temperature is related to the photon temperature in this way. And remember that this 4 divided by 11 has to do with the entropy degrees of freedom, okay, that were around at the time before E plus E minus annihilation and after, okay? Now, at sufficiently early times when the temperature of these neutrinos is still a lot larger than the neutrino rest mass, so you have relativistic neutrinos, then having the neutrino temperature also allows us to relate the energy density in the neutrinos to the energy density in the photons. And roughly, you just make use of the fact that you have Fermi-Dirac distribution, relativistic Fermi-Dirac distribution for the neutrinos. They have this temperature over here, so we expect the neutrino energy density to go like T nu to the 4th multiplied by some prefactors, and that can be related to also the photon energy density because you have a T gamma to the 4th over here. Okay, so if you evaluate this thing numerically, you have 0.227 per family of neutrinos and antineutrinos, and if we sum over all 3 families within a standard model, then the number that pops out here for the energy density ratio is 0.68, which is precisely that 10% versus 15% in the pie. Now, so that's a prediction, but there's a common thing that people do in cosmology, and that is we like to parameterize this neutrino to photon energy density ratio in terms of a parameter called N effective. Okay, it's called the effective number of neutrinos. And essentially what you do is that instead of putting in 3, you just call that N effective. Okay, and this lump of stuff here is essentially the energy density in one thermalized species of 2 masses, of massless fermions with 2 internal degrees of freedom with the temperature corresponding to this T nu 4 divided by 11 raised to the 1/3 T gamma. Okay, so that's that. And N effective is it's just the effective number of neutrinos, and within a standard model, this number is very close to 3 because we have 3 families, right? Okay, but it's not an integer. And the reason it's not an integer is that ultimately the definition of this N effective is an energy density ratio. Okay, so that number could be anything real. And in fact, it's a number that can be calculated very well. And the number it takes on that we know at the moment is about 3.044. There's even some error bars around it. As said before, the 3 here is just standing for 3 families of neutrinos and antineutrinos. And this percent level correction here comes from a whole lot of standard model effects like loop corrections, finite temperature corrections, etc. I'll say more about this in a bit. Okay. Now, since we can define the energy density ratio in neutrinos in this way, yet another common thing that people have been doing in recent years is to reinterpret this N effective parameter to describe also other light thermal relics. And the reason why this is possible is that if you have a BSM theory, I don't know, axions, let's say, thermal axions, let's say, which is light, so light in the sense of being sub-electron volt in mass, and it's feebly interacting, and you manage to produce a whole lot of these things in the early universe by scattering. Then, as far as cosmology is concerned, this light relic will look exactly like a neutrino. Okay? So we may as well lump all the neutrino energy density together with this light relic energy density together and call this thing altogether N effective. Okay? So the standard model value will be 3.044, but if you say you have axions, let's say, then this number could be 3.5. Or if you have a thermalized like sterile neutrino species, you could have N effective of 4 even. Okay? Right. Now, why is N effective interesting and why is it relevant for cosmology? Well, first of all, what you're doing really if you increase or decrease N effective is that you are increasing the energy or decreasing the energy density in light relativistic stuff. And since the expansion rate, h squared, the Hubble rate square, is directly proportional to the energy density of the stuff in the universe, what this means is that if you change the N effective, particularly if you do so in the early universe when radiation dominates, you can have a huge effect on H. Okay? And that's something that is observable. Okay? In particular, if you look at the light element abundances and the CMB, the changes that that N effective induces to the Hubble expansion rate can be felt by these processes. Okay? So, first of all, let's just talk about nucleosynthesis. So, nucleosynthesis, as mentioned earlier, is basically a network of nuclear reactions where you start with neutrons and protons, and then once these nuclear reactions once the energy drops down to a low enough point when photons are not breaking up in nuclei anymore, then you'll have these nuclear reactions happening. So you combine neutrons together with protons to form a deuterium. You can go to other isotopes of hydrogen like tritium. You can even form helium in these various isotopes, as well as other light elements like lithium and beryllium. And these processes were supposed to have taken place at a temperature of around 10 keV to 100 keV. And recall that neutrinos decouple at 1 MeV. So basically what you should have in mind is neutrino decoupling followed by BBN. Okay? Now, key thing here is that these are nuclear reactions, and so the expansion rate would be something that matters for how effective these reactions are. Because remember that we compare lambda gamma, the interaction rate per particle, with H, right? So if you change the expansion rate, you will definitely have an effect on these interactions. Now, as it happens, the largest effect that expansion has is on helium-4. And the reason is because if I look at all of these light nuclei over here, the most stable of these nuclei is helium-4. Yeah, the binding energy is the one that's the most favorable for the helium. Of all the elements here, that's the one that's most likely to be formed. Which also means that if you start with a soup of neutrons and protons, then most of the neutrons will actually end up bound in the helium-4. Okay, and the neutron to proton ratio itself depends on how expansion affects what I call the beta processes. Okay, so these are the beta processes. So you combine an electron neutrino with a neutron, you get a proton and an electron, and there's also this analogous process here for the anti-neutrino. Okay, so these processes are happening at around MeV 100 keV temperatures, and they can go out of equilibrium if the expansion is too fast. Well, yeah, they go out of equilibrium more quickly if the expansion rate is too large. Conversely, if the expansion rate is kind of low because your N effective is low, then these processes can stay in equilibrium for a longer time, and that would end up changing the neutron to proton ratio. Okay, so here's a picture here that I took from a recent BBN review by these guys. And what you see here is basically the abundances in various light elements. So you're starting with black line is neutron. The red line here is a hydrogen, so that's just a proton. And, deuterium, tritium, so on and so forth. And a very nice thing here you can see is that this is the hydrogen. So hydrogen is always the most abundant element in the universe. And the black line here is the neutron, okay? And so what's happening here is that it's kind of dropping as because neutron can decay. And then at this point, you have a sharp drop. But concurrently, you also have this blue dashed line here going up really, really sharply. And that's because all the neutrons are being sucked up into helium-4 nuclei. Okay, so that's what's happening. Here's another picture taken from also a fairly recent review. And what we're seeing here is the abundances of various light elements. So this is helium-3, this is lithium-7. Two lines here are helium-3 and deuterium. And YP here is called a helium-4 mass fraction. Basically the helium-4 abundance, if you like. And what you see here is the abundances of these various nuclei versus the baryon to photon ratio, which is also an important parameter in BBN because that basically determines when BBN should start. CMB mesh evaluate here. And the interesting thing to note here is the top plot where we have the helium-4 mass fraction, and there are also 3 lines correspond to N nu is equal to 2, N nu is equal to 3, N nu is equal to 4. N nu is our N effective. Okay, so you can see that the helium-4 abundance is quite strongly dependent on exactly how many neutrinos are thermalized. Okay, good. This is a recent, okay, actually, if you go back to this picture here, you can already see that that's the measurement, and it's favoring N effective of 3. Okay, but of course, you can also do these analyses more carefully, and that's the one done by these guys here. They looked at the helium abundance, which is the blue line, this one, that's a constraint in N effective, and omega B is the same as the baryon to photon ratio. That's the exclusion region from deuterium, and if you combine them together, you get the red ellipse, okay? And the preference at the moment is for N effective of 2.88 plus or minus about 10%, so that's incredibly close to the prediction of 3. Yes? Yeah, yeah. And it has to do with, this equilibrium, okay? So, so to determine the neutron to proton ratio, that goes like essentially the mass difference between the 2 nuclei divided by T. So it changes with temperature. And the lower the temperature, so let's see, if you have a, so it's a question of when these processes freeze out, okay? So then you freeze in this number, and so the later it freezes out, the smaller the T is, and therefore the larger this is, and therefore the smaller this is. And then you have to worry about neutron decay. I mean, I'm probably not, I'm thinking out loud here. I don't have the full argument. Right? We can look at it later on if that's okay. Okay, because I get a bit confused myself sometimes about which way things go. I have to put it down on a piece of paper and I look at it again. But it's basically that kind of argument. Yeah. Okay, where were we? So that's the BBN. Okay. Now, you can also measure N effective in the CMB, and in fact, most people these days talk about CMB constraints on N effective anyway, because it's kind of perceived as being a bit more reliable. Okay. Now, and again, the reason why N effective affects the expansion rate is that when when the CMB anisotropies were formed, you are looking at an epoch that is just a little bit after metal radiation equality. So you're still sensitive to the radiation content. Okay, so that's why N effective can be probed around the CMB epoch. Okay, now some of you probably played with codes like CAM or class. These are codes that are used to calculate anisotropies in the metal power spectrum. You can just download them. They're black boxes, but you can just download them. Now, if you go to the initial parameter files and plug in an N effective that is different from 3, then this is what you'll end up getting. You will have, so blue line here is N effective of 3, and if you change it to 10, then you get this huge change in the CMB anisotropy power spectrum. Unfortunately, that's not the real effect of N effective. And the reason it is not the real effect of N effective, and the reason why it is called a naive signature, is that we are also using exactly these same measurements to pin down another 6 parameters. Because we don't really know what the dark matter density is. We know about it from the CMB. Okay? We are also not sure what Hubble parameter is, or baryon density, or any of the inflation parameters. Okay, so we're all relying on the CMB to pin down those parameters. So what this means is that when you try to determine the effect of M effective in the CMB anisotropies, you need to worry about degeneracies between these various parameters. Okay, and in particular, N effective is strongly degenerate with omega M, which is the meta density. It is also very, very degenerate with the Hubble parameter H. Okay, so if you increase your N effective, it is possible to tweak your meta density and your Hubble parameter so that everything looks more or less the same as your original signature. Okay, so this is only the naive signature. The irreducible signature of N effective, however, it does exist. It's not like it's the degeneracy is complete. And in fact, the irreducible signature of N effective is in the damping tail. So this is a paper from 2013 by Lloyd Knox and his group, Davis, UC Davis. And what they've done here is to plot the CMB anisotropy power spectrum for these rather high multiples, so 500 all the way to 2500. And what they've done here is that they change N effective between the very N effective from 2 to 6, but at the same time, they also tweak other parameters like omega M and H, such that you have a pretty good matching of the first couple of acoustic peaks, the first one definitely, and to a large extent here as well. But then you see that these scenarios start to deviate once you go to a large enough multiple. And this is what we call the irreducible signature of N effective. It's in the damping tail. That's it. And roughly what's happening here is that you have this, what is called diffusion damping. And it comes about because when you look at photons, they are in around the CMB formation epoch. They are kind of doing a random walk in an electron soup. Okay, when you have a random walk, you have diffusion. Okay? Your electrons are, your photons are basically diffusing in the electron soup, and that diffusion will wipe out any anisotropies that are on scales smaller than the diffusion length. Okay, so it's called diffusion damping, which is why you have this kind of drop, decaying away of the power as you go to large values of L. It's damping. And the diffusion damping scale, that's a rather nice expression you can write out, looks something like this. It depends on the Thomson cross-section, the free electron density, which makes sense because your photons are diffusing, and you want to know what is the mean free path of this thing. And then you have the Hubble expansion rate, H, that enters into the expression, so that depends on the N effective. Okay? So that's how N effective affects the diffusion damping scale. And then there's a bunch of factors here as well that depends on the baryon to photon density ratio. So using this effect, we also have a bound on N effective from CMB, and it is around 2.99 plus or minus 0.34. So again, this is incredibly consistent with the standard model prediction. Right. Yeah, your sterile neutrino is very problematic in that case. Yeah. Okay, so that's the observable signature of N effective. Now, I mentioned earlier that the standard model prediction for this N effective parameter can in fact be calculated very precisely. So I'll just say a couple of words about that now. Okay, so at the moment, the standard model prediction is this number, 3.0440, plus some tiny error bars that was investigated in a series of papers in recently, and it includes one of our organizers here, who was an author on this paper. And, huh? I think Akita did, actually. The better 2019 was earlier. Fair enough. That's fair enough. Yeah. Okay. So so there are some percent level corrections to this number. So it's not exactly 3. There are some percent level corrections, and essentially these corrections come about because of these various effects like non-instantaneous neutrino decoupling, flavor oscillations, non-relativistic electron gas across the neutrino decoupling, also finite temperature effects. It's a mouthful of words, so let me just try to explain it in this schematic. Essentially, you have these corrections because this picture here is not completely correct. Okay, so I use this picture here to determine this relation between T nu and T gamma, but there are actually a lot of approximations going into this prediction. And the first one is that we treated decoupling and E plus E minus annihilation as distinct events. Okay, we just said decoupling happens here at 1 MeV is instantaneous, annihilation happens at 0.5 MeV is instantaneous as well. But in reality, that is not true. Both of these events are kind of spread out over time, such that they overlap. Okay? So in other words, what it means is that when E plus E minus annihilation happens, some of that energy that's dumped into photons will in fact be shared with the neutrino sector. Okay? That was not the assumption before, but in reality, some of the energy density some of that energy will be passed on to the neutrino sector. Okay, so that's the first thing. The second thing is that when we wrote down the entropy in the QED plasma, we just said this is 11 divided by 45, blah, 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 blah. Okay? And when we made that assumption, when we wrote this expression down, there was another assumption in there. We treated the electrons and positrons as totally relativistic, which is also not quite true if you are very close to the annihilation epoch. So we should take into account the fact that the electrons are actually slightly massive. Okay, that also changes this expression. Okay, so all in all, having these deviations from my assumptions means that in the end, by assuming a temperature relation between the neutrino temperature and the photon temperature in this way, plus the Fermi-Dirac distribution, actually does not completely capture the neutrino to photon energy density ratio. Okay? We need to do more. So what do we need to do? So first thing we need to do is to try to track the non-instantaneous decoupling. In other words, we want to track the fact that the decoupling epoch overlaps with E plus E minus annihilation. And the way to do that is through the Boltzmann equation. Okay, so actually not completely, but anyway, just this is the Boltzmann equation, and it's essentially an equation for equation of motion for the phase space density of the particle species that you're interested in. So if you're interested in particle species 1, you write down the 1 particle phase space density, and this thing here will be equal to some Poisson brackets with the Hamiltonian to describe the propagation of the particle. And there will also be a collision term which describes scattering processes or decay or annihilation and whatever. They all go into here. Now, I'll tell you what these things are in a bit, but the collision term essentially is something that looks rather ugly. You will have this is Lorentz invariant, and you have this energy conservation, energy momentum conservation part here, which is denoted by the Dirac delta. The matrix element of the scattering process will be here in m squared, and there's a bunch of phase space factors that account for how much of stuff is being scattered into one particular state or being scattered out. Okay, and you have these quantum statistical factors as well to describe things like Bose enhancement and Pauli blocking. Okay? Now, that's actually that's not what you normally do if you were interested in things like, I don't know, dark matter production, which probably some of you do. The case of neutrinos is slightly uglier, and that's because we also need to take into account the fact that there's flavor oscillations. Okay, so essentially what it means at the technical level is that instead of using a Boltzmann equation that looks like this, you need to promote all the phase space densities to density matrices. Okay, and the density matrix looks something like that. So this is for 3 flavors, if I'm interested in a 3 flavor case. And the diagonal terms here are essentially the occupation numbers, so the same as the phase space distributions. And you also have a bunch of off-diagonal elements here, which are there to describe the oscillation phases. Okay? So that's what you have. It's an operator, so you have to take the commutator of that with Hamiltonian, and the Hamiltonian, which is over here, and you'll probably recognize this. This is a Hamiltonian to describe vacuum oscillations. Okay, the first part, that's a mixing matrix. These are the masses of your 3 mass eigenstates. Mixing matrix again, Degas. And if you have any matter effects that might be present in the early universe, and that there definitely is, you have to put that here as well. Okay, so any kind of coherent forward scattering would go in here. And again, you have the collision term that appears in the equation of motion. So all of this system equation is called a quantum kinetic equation, if you like to give it a name. Okay? Now, just to highlight the collision term and the matter density again. Remember earlier, last lecture, I talked about all the interactions that are present in the universe, all the particles that are present there between temperatures of 0.1 to 10 MeV, and a lot of them involve the neutrino. Okay, so all of these processes could also give rise to order GF forward scattering terms. Okay, that would go into the matter potential, and all the GF square terms will go into the collision integral. Okay, so basically these processes go into the collision integral and the matter density. Now, you can. This is usually what's. I mean, if you look at all the codes that are, what the analysis that are around at the moment, most of them will just take into account these processes at tree level. But if you're crazy, like some people are, including myself, then you might also ask what happens to these collision integrals at next to leading order. And in particular, at recent times, there have been a bit of interest in computing QED corrections, quantum corrections and finite temperature corrections to these rates. So essentially, in terms of a Feynman diagram, here you have a contact four Fermi interaction, so neutrinos scattering off an electron. And what we're doing here is essentially to consider what happens if there are QED corrections to any of these electron lakes. So that's a loop, self-energy here, a vertex correction. This is a closed fermion loop. And this diagram here accounts for any kind of absorption and emission of a photon from the bath. Okay. There are some various claims in the literature about the importance of these diagrams. There's one group that claims there's a significant effect, and then there are other people who claim that there are not much of an effect due to these NLO corrections. So there's no complete picture yet. It's a work in progress. So hopefully next time you see me again, I'll tell you more about it, about the status of this. Yeah. 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 Yeah, it is pretty complicated. There are a couple of codes around at the moment, which I'll get to in a bit, that have actually coded up the entire set of equations, full momentum dependence. So there are people who are specialized in coding these things up. Yeah, it can be done. Yeah. Well, supernova is much nastier, I would say. This is still relatively easy because you're homogeneous and homogeneity and isotropy is still relatively easy. Yeah. Yes. Yeah, yeah. Astrophysics is much nastier. Too much. Things are changing all the time. Cosmology, you can always say static, quasi-static in a lot of places. The QED plasma is in thermal equilibrium, so it completely simplifies. So it's doable. Yeah. Um, okay. So that's ineffective. But let me just also mention, for those of you who are interested in sterile neutrinos, the QKE formalism with the density matrix can also be used to compute sterile neutrino production. Okay, it's exactly the same formalism. Okay, and you can use it to calculate the thermalization of light sterile neutrino states motivated by the short baseline anomalies. Okay, this 1 electron volt sterile neutrino that people like to talk about sometimes. And of course, there's also KV sterile neutrino dark matter. The formalism used to describe the production of these things is also the QKE formalism. Okay, and these are the similarities to the standard model neutrino case. The differences between sterile neutrinos and standard model neutrinos are, of course, that the sterile states have no matter effects or collisions. So you need to change the matter effect terms a little bit. You need to change the collision terms a bit. And also, in the case of KV sterile states, they are produced much earlier at maybe like 100 MeV in temperature. So the content of the universe at that time is also different from the content of the universe at about 1 MeV. Okay, so there's some minor differences, but the formula is the same. Yeah.
For instance, the neutral current affect the ordinary states, but not the sterile neutrino. There is some relative effect.
Oh, I mean, so what you can do, if I go back to the formalism, is that all I mean is that when you have meta effects, your last entry for the sterile neutrino will just be 0. But of course, there's mixing.
Yeah, but it's 0 for sterile. But what counts is the difference of effect from active and sterile.
Sure.
And there is effect.
Oh, absolutely. Yeah. But through mixing. But the thing is that in my formalism here, the mixing is taken care of by the oscillation Hamiltonian. And if I'm purely asking, do I have this is 3, but I can add the fourth one, right? I can do M1, M2, M3, M4, and the matter effects for this part would of course be 0, and my collision integral will be directly will be in the flavor basis. So I will look at like new E scattering, yeah.
So matter effect here,
Yeah.
I agree with this is 0.
Yeah.
Here is non-zero.
That's right. Yeah.
So this is different from 0.
That's right.
It was explained by Gabriela. Since what counts is the difference, you can even do the contrary.
Yeah, absolutely. But I agree. I completely agree with you. But at the differential equation level, I don't have to worry about this. Yeah, if I do an analytical solution, I agree that you have the mixing angle and there will be effective scattering, if you like. I mean, this is like Dodos and Woodrow. Yeah. Through this is at the level of V matter, it is 0, and of course, ultimately you do produce a sterile neutrino, so something is happening effectively. It's just that at the level of writing down my equation, I will have a 0 here. Yeah, and at the level of writing down my collision terms, I will also have 0 for the terms that are proportional to the that are for the sterile neutrino. That's all I mean. Yeah. Right. Okay. So where was I? Sterile states. Okay. And another aside is that you could also think about non-standard neutrino interactions, and that would be essentially any kind of interaction that is beyond weak interaction. So what you have to do is to look at how NSI can change the scattering and annihilation rate through the collision integrals. You can also have additional meta effects due to NSI through the oscillation Hamiltonian. Okay, I'm not going to say more about this because I think Sergio Pastor will be here next week. I think he's going to talk about this. Okay, bottom line is that having these non-standard interactions, you can change this N-effective parameter as well. Okay, so also mentioned earlier is that there are actually some publicly available codes that you can go and download, so you can do it yourself. Neutrino decoupling. There are 2 codes that are available at the moment that I am aware of. One is called Forte Piano. It's written by the Valencia group. Stefano Gariazzo is one of the main people who is also going to be here next week, right? And it's a code that takes into account 3 active and 3 sterile neutrinos. That's the plus, okay? The drawback is that it's CP symmetric, so they don't do lepton asymmetry. But it has a precision mode that includes corrections to the QET equation of state to order E cubed, and you can download it here. Another code is called lasagna. It comes from Thomas Tram in Aarhus, in Denmark. It's 1 active, 1 sterile, so it's a bit limited, but it can handle CP asymmetry. So they wrote it to look at lepton asymmetry generation. And here's the place where you can do the download. Okay. Okay, so that's the QKE. One more thing I want to mention is the second place where this picture has gone wrong, and that is over here. Okay, so I mentioned that here in this expression, when we calculated the neutrino temperature, we had to write down the entropy density for the QED sector, and I wrote it down like this. And the implicit assumption here is that the electron and the positrons are actually massive. Okay. And also, we had to assume that this is massless. Okay. And we also assumed that the QED plasma was an ideal gas. Okay. That there are 2 assumptions: massless neutrinos and an ideal gas. But both of these assumptions can become bad if I'm interested in percent level corrections to the QED plasma. Okay. So, and the reason is as follows. If I look at the QED plasma, you have all these scattering processes that are happening. So you can have gamma scattering of electrons, you can have E plus E minus annihilation, gamma gamma. Okay, so they're interacting all the time. Okay. Now, if I am looking at an ideal gas, then essentially what's happening is that you have particles that are moving in straight lines, and then they hit each other. The scattering happens instantaneously and over a very small volume, and then after the scattering, they all move off in a straight line again. Okay, so that's the ideal gas approximation. Particles always move in straight lines, and the only thing the scattering does is that it will change the direction of these lines into different lines. Okay, so if I'm to calculate the energy density of this ideal gas, what I'm doing essentially when I take the phase space distribution and integrate in momentum is that I'm just summing the kinetic energy of all the gas particles in the gas plus the energy due to the rest mass of these particles. That's what the energy density is, okay, in the standard Cope-Turner, integrate your phase space distribution kind of approach. You can also figure out the pressure, and pressure in this case, in the ideal gas case, is essentially just the kinetic energy of the ideal gas particles that are moving around in straight lines. But as said in the previous slide, there are these electromagnetic interactions between the electrons and the photons. So what this means immediately is that think about an electron. It's moving in this photon bath. And this photon bath actually presents a kind of resistance to the electrons. Okay, so it's kind of like a mass. You have to move through it, it's scattering. So you have this kind of refractive index effect of the photons on the electrons. And you also have a similar effect of the electrons providing refraction for the photons. So in the end, what you have when you consider these interactions is that you have these temperature-dependent dispersion relations, okay, for both the electrons and the photons. Furthermore, if I have something here that is providing a potential, electromagnetic potential, and you have another particle that is feeling that potential, then you will also have forces, okay? And these forces can tend to, change the paths a little bit so that you don't have straight lines, but the paths are slightly bent, okay? So if I take into account all of these things here, what it means is that when I compute the energy density, what I'm computing, what I need to take into account, is the modification to the kinetic energy due to these interactions, plus any kind of rest masses that is modified by these temperature effects, and there will also be an interaction potential energy between the particles. So this is significantly more complicated once the interactions are taken into account. Similarly, from the pressure, we have modified kinetic energy, and there will also be modify a pressure coming from taking into account the fact that these forces are in place. Okay, so overall, what this means is that once you take into account these interactions, the QED equation of state will be different from the ideal gas case. Okay. So that's a very hand-wavy explanation. If you're interested in calculating diagrams, that's the lowest order QED correction to the QED partition function. That's this thing here. You can go calculate it. Yeah. What? Sorry. Yeah. Oh, but if you don't find a temperature, if you do find a temperature corrections, you're doing in. Yeah. So that's so this is a first. The sunset diagram is the first correction to the QED equation of state. Yeah. Okay, the first, I mean, the leading order effect is of course just ideal gas, and that's the first correction that you have to the partition function. Okay, that's all I want to say about that. But let me just summarize. Here are the numbers we have. So all of these corrections that are there and how they contribute to changing this number, and also some uncertainty to this number, which comes from numerical resolution of the code, plus uncertainties in the input parameters. Okay, so that's my summary. And for part one, okay, I'm going to stop here and ask anyone if there are questions, because the next part, which I'll begin, will be completely different. Yeah. Dark matter. Dark matter at 1 MeV would have such a tiny energy density that I can just not do anything about it. I can ignore it. Right. Well, I mean, okay, so it depends on what you're trying to do. If I'm interested in producing dark matter, then of course I would focus on looking at the energy density in the dark matter. But here, the N effective calculation, we normally don't worry about the dark matter because we know that during that time we have radiation domination. And if I know what the dark matter is today and I scale it back in time, it's so negligible that I don't need to worry about including that contribution in any of these calculations. Yeah. You won't see it. It will be so highly suppressed by the fact that you have, suppressed by the fact that your dark matter energy density at that time is negligible. Yeah, it would be, it's in the same way that we don't care about scattering on neutrons, for example, or protons. Okay, the dark matter density would only be at most 5 times more than that, right? And we don't take that into account because these are suppressed by I don't know 10 to the minus I don't know 20 or whatever at those times. Oh right, okay, that. Yeah. Yes, at later times, yes. At so for calculating the standard model and effective parameter, you don't have to worry about dark matter. But once you are looking at CMB times, you do need to worry about dark matter because CMB happens more or less around matter radiation equality. So radiation matters, dark matter also matters. Yes. Yeah. Absolutely everything. It doesn't matter. Yeah. Yeah. No. So if you talk axions, let's say, for argument's sake, axion dark matter is not thermal. Axion dark matter that you produce via phase transition is extremely, extremely cold. So you think about Bose-Einstein condensate, it's occupying the lowest mode. These, when I talk about thermal axions, we're talking about axions that are thermalized by scattering, and so they'll have a temperature, and they're occupying a much higher end of the momentum distribution. So light dark matter is by definition very, very cold. Otherwise, if they're thermal, they can't be the dark matter. Yeah. Yeah. Yeah.
But shouldn't that term be included the temperature, meaning that what is really changing is the temperature of the fluid?
Well, I wouldn't say that because temperature is a very particular parameter. Temperature, technically, you can't even define the temperature when you don't have equilibrium, right? So the treatment, I mean, what you should really be looking at, if I ignore oscillations, what you should be looking at is the one particle and phase-space distribution. That's the more fundamental parameter. The temp,
So let's say we are able to measure some time
yeah,
the temperature increase.
yeah.
How we develop temperature?
But I never really measure the temperature. You see, that's the point. What you're measuring, even when you look at a CMB measurement by Kobe virus, what they were doing is to measure the Planck spectrum. And they fit the Planck spectrum and say, hey, that's a fantastic Planck spectrum. It's described by a temperature parameter. Yeah, I mean, a temperature itself is not something you measure. Okay, so you measure whatever is the flux in different frequencies that come in, and then you infer from that what the temperature is. So the temperature parameter is not actually terribly fundamental. And what we do here in these decoupling scenarios is that we go straight to the phase-space density, and we totally ignore the temperature parameter because that's not terribly meaningful. It's only meaningful when your phase-space distribution is nice and in a thermal equilibrium shape. Then you can re-parameterize that into the temperature parameter.
So you would measure then spectral distortion.
Yeah, if I can measure, yeah, exactly. I mean, in the case of CMB, that's exactly what people do. They can actually measure the whole spectrum. They can, in the future, hopefully with some improved measurement, you can probably even measure spectral distortions as well. Like right now, spectral distortions are highly constrained. Yeah, but the fundamental thing is the spectrum, not the temperature parameter. Anyone else would like to ask anything before I totally switch gears to something else? So I have seen people use that to look at neutron anti-neutrons. I've seen that done in the context of leptogenesis, so that's still neutrinos, but kind of yeah. But yeah. So basically, it's anytime you have any kind of mixing between states, and you also have scattering processes as well, you would need to bring this out. Yeah. So yeah, definitely, it's not just in neutrinos. Definitely the I mean leptogenesis, as I said, neutron, anti-neutron. What else? Yeah, condensed matter people use it all the time. Uh, Definitely. So right. Uh, Anything else? I'll move on then. Maybe I should move on. Oops. Right. So part two, I am going to talk about neutrinos in an inhomogeneous universe. So you can see the progression of things. I'll say today a bit about the theory of inhomogeneities, and then tomorrow I'll talk more about how they apply to neutrinos and structure formation and other things. Okay, so we're looking at basically what happens here at around the CMB epoch and large-scale structure epoch. Here we go. So just an overview. So far, in all our discussion before, we have assumed the universe to be homogeneous and isotropic, but in reality, this is of course not true. We have galaxy distributions, which clearly indicate galaxy distribution that clearly indicates that there are places that are denser and places that are less dense. And this picture here is a simulation of the intergalactic hydrogen cloud that people did to study the Lyman alpha forest. CMB is, of course, also not homogeneous because we've seen these fluctuations in the temperature that are of order 10 to the minus 5. Now, to describe these inhomogeneities, basically the consensus picture that we have at the moment is something like this. So this is time going down, and you go up, you're going very far back in time. And in the current theory, we have an inflation epoch, and so inflation solves a number of things. Flatness problem, monopole problem, horizon problem. But one cool thing about inflation is the way it's implemented with a scalar field at the moment, is that you can also have quantum fluctuations developing on the scalar field. And if you have these quantum fluctuations and you suddenly stretch out space by a lot during the inflation process, then these quantum fluctuations will also get stretched out to very large scales, and they become classical fluctuations on the space-time metric, or the space-time fabric. Okay? So in other words, inflation at the moment provides the initial perturbations on the space-time metric, and they also provide the initial conditions for CMB and large-scale structure. Okay, so there will be, imagine the space-time fabric having peaks and peaks and troughs everywhere, and these are essentially the seeds for structure formation and the perturbations that we finally see in a CMB. Now, inflation was supposed to have taken place a very long time ago, and then the universe evolves forward. And what happens then is that you would have gravitational effects. So there are regions that are dense, and what gravity would do would tend to make these dense regions even denser. Okay, will clump things. But at the same time, if the stuff that you have in the universe is also moving very fast, then they will also have pressure. So you have a competition between pressure and gravity, where gravity would tend to want to pull things in, and pressure would like to push things out. Okay, so there's a nice competition between these two. And that takes place all the time, during all this time, across the matter radiation equality epoch, and then you have photon decoupling. And finally, we see these perturbations as CMB anisotropies, which correspond to perturbations in the photon energy density and polarization. And we also see perturbations in the non-relativistic matter. Okay, and the perturbations in the non-relativistic matter are the things that eventually become galaxies and galaxy clusters. Now, to track these processes of how CMB anisotropies form and how perturbations grow, what we need to do essentially is to supply a framework that consists of using perturbative general relativity plus a Boltzmann equation to describe how stuff evolves under gravity. Okay. So just to give you an idea of what we're looking at, here is this schematic that we've seen before. That's time over here, and we're interested essentially in this epoch. Okay, so more or less in matter domination between a redshift of about, say, 5 down to the present time. Okay, pretty low redshift stuff. Okay, so how do we actually implement this framework? So we have seen earlier that in a homogeneous and isotropic universe, you write down FLRW metric. Okay, that's your space-time geometry. There's also a corresponding stress energy tensor, which is diagonal. But now I want to extend this framework to describe inhomogeneities as well. So what I'll do is to perturb around the FLRW space-time. So in other words, when I write down the metric, I'll write down G mu nu. I will have a main term here, which is the FLRW metric, okay? And then there will be some tiny perturbations here. That's the gravity part. And these are perturbations, H mu nu is a perturbation to the metric in the sense that the absolute values are much less than 1. We do a similar thing also with the stress energy tensor. We split it up in the homogeneous part, and there will be a tiny part here which corresponds to perturbations in the energy density, in the matter, okay? And again, it's a perturbations in the sense that these entries here, delta T mu nu, must be much less than the energy momentum, energy density of the homogeneous energy density. Now, if we do perturbation theory, then of course you can perturb to very high orders. But as far as calculating things like large-scale structure and CMB anisotropies is concerned, these are things that happen on pretty large scales. So linear perturbation theory normally suffices, okay? So then all we have to do is to take Einstein's equation, stick in my metric, and find out my Einstein tensor, stick in my delta T mu nu to find out the stress energy tensor term, and that together would tell me how the perturbations in the metric evolve according to the perturbations in the stress energy tensor. Okay, that's the Einstein's equation. And I mentioned earlier, we also use the Boltzmann equation. And what the Boltzmann equation does is to tell us how the perturbations in the stress energy tensor evolves due to perturbations in the metric, as well as the properties of the stuff that is being considered. Now, so here's the metric again. It's a 4x4 matrix and symmetric. Okay, so as usual, we know that the perturbations here would have 10 degrees of freedom. Okay, just counting 16 entries, but symmetric, so you reduce down to 10 degrees of freedom that are actually independent. However, not all of these 10 degrees of freedom are meaningful. And that's a consequence of the fact that we, using this covariant approach, and anything formulated in a covariant way has a lot of redundancy. Okay? And in fact, here there are 4 degrees of freedom in the metric that are just called gauge degrees of freedom, related to how we choose our coordinate system. Okay? So if I remove these 4 degrees of freedom, just gauge degrees of freedom, then in the end there are only 6 degrees of freedom that are actually describing physics. Okay? You can further break down these 6 degrees of freedom, 6 physical degrees of freedom, into scalar, vector, and tensor modes. Okay? There are 2 scalar modes, and these are the 2 modes that are relevant for structure formation. I mean, I'm not deriving anything here, just telling you as facts. Sorry, you just have to accept it. And then there are 2 degrees of freedom called tensor modes, which are essentially gravitational waves. Okay, the 2 polarizations of a gravitational wave are the 2 tensor modes. There are also 2 vector modes, but in standard inflationary lambda CDM, the vector modes are not present because we don't make them during inflation, and even if you make them, they decay away anyway, unless you have magnetic fields or whatever, which is also not standard lambda CDM, so we ignore those. I will only be saying things about the 2 scalar modes. So if I just keep the 2 scalar modes, then one way I can write the metric perturbations is in this manner. Okay, so I have something that largely looks like FRW, but then there's also a perturbation part psi and a perturbation part phi over here. So these are meant to be small. And there's a name for this way of writing down the metric. It's called the conformal Newtonian gauge. It has this funny name because if you compare this expression over here with the weak field metric, which you've probably seen in your introductory GR class, they look very similar. Okay? And the weak field metric is the one that we use to study things like perihelion shift and light deflection and lensing. Okay? So, this potential here essentially is just a Newtonian gravitational potential, which is why it is that the Newtonian gauge is kind of nice to use. So I'll use that in the following. Now, here's the stress energy tensor, and I said we have to perturb that as well, okay, because there are perturbations in my matter and my energy, okay. And it looks something like this. So this is here the unperturbed part, which is the one that we saw yesterday for FRW. And here are all the perturbations. So what do we have? You have density perturbation over here. You have pressure perturbations as well in the diagonal. And then you could have velocity perturbations that enter here in the green. And in addition, you could have these off-diagonal terms in the space-based part of the stress energy tensor that correspond to anisotropic stress. Okay? Now, that's roughly what they look like. Now, in standard inflationary lambda CDM, we are only interested in 4 forms of matter and energy. Okay? We have cold dark matter, we have neutrinos, we have protons and electrons, we have photons. And so this schematic here shows you how they interact with each other. Now, these 4 forms of stuff look like random things, but actually they're not. And that is because, essentially, they just correspond to limiting behaviors. So cold dark matter is a non-relativistic, non-interacting kind of stuff. Neutrinos, if they're massless, are relativistic and non-interacting kind of stuff. Photons are relativistic and interacting. And the protons and the electrons are non-relativistic and they're interacting. Okay? They're interacting amongst themselves via the Coulomb potential between themselves. There's also Compton scattering between the electrons and the photons, or the electrons, rather. Okay? And for each kind of stuff that I can write down a Boltzmann equation, which looks something like this. Okay, so you'll be tracking the phase space distribution of these things. The gravitational effects would enter through the Christoffel symbol here. And on the right-hand side of the Boltzmann equation, you have all the non-gravitational interactions, like all the scattering. Compton scattering would go in here, etc. But of course, all forms of energy densities will interact with the space-time metric, which is indicated by these orange dash arrows here. And of course, that would just mean that we have to take into the perturbations of these things and then feed it into the Einstein's equation to see how that changes the metric. There's a set of equations you can write down to describe the whole system. I'm not going to explain any of this, but if you are interested to find these equations, here's the standard reference. So you have the metric, stretch energy tensor, the Boltzmann equations for different things, Einstein's equation to relate the perturbations to the metric perturbations. Now, those of you interested to play with this kind of system, there are a couple of codes at the moment that are very popular. One's called CAM and the other one's called class. They are mostly optimized for doing standard inflationary lambda CDM, but you can fairly easily modify them to accommodate exotic models as well. And further information on cosmological perturbation theory you can find in these lectures. I'm almost there. Now, so far that was standard lambda CDM and where the neutrino was massless. But of course, in reality, we know neutrinos are massive, right? So we do have to change this picture a bit. But the change is somewhat subtle, and that is because neutrinos, as we know them today, are sub-electron volt in masses, which means that they are initially relativistic and then they transition into a non-relativistic state. And that transition happens at a redshift of about 100 to 1,000. So technically, these neutrinos are non-relativistic today, but they're not exactly cold. Okay? So what it means is that you can't really just call them cold dark matter, nor can you treat them as completely relativistic stuff. And in fact, what you need to do is to track the transition from relativistic to non-relativistic behavior. Okay? And that complicates things a bit, actually. But the complication arises at the implementation level. At the fundamental level, you're still using the Boltzmann equation to do the tracking, so there's no fundamental difference between tracking massless and massive neutrinos. The only thing that differs is that every time you add a mass to your equation, you're introducing a new energy scale, which translates into a time scale in your problem. So essentially what this means is that you need to track the Boltzmann equation in its entirety with the full momentum dependence and how each momentum goes non-relativistic over time. And that, from a practical point of view, means that you have normally about 10 to 20 times more equations to solve for a massive neutrino calculation relative to a massless neutrino calculation every time you add a new mass. So if you want 3 different masses, we're talking about 60 more equations, 60 times more equations that you need to solve. So that makes it kind of ugly. So if you next time you read a cosmology paper and look at, why don't they look at the full mass hierarchy? That's the reason. It takes so much more time to do 3 different masses compared with just 1 mass, or compared with no mass at all. Okay? Yeah. Yeah, that's right, yes. In the CMB, it's all mass basis. Yeah. You can do it in mass basis if you want, yeah. So once you're looking at CMB physics, you don't care about flavor anymore because there's no neutrino scattering, at least not in the standard case. If there's no scattering, then there's no need to worry about the flavor basis. So you just do everything in the mass basis, and that's it. Uh, well, you wouldn't. You wouldn't. Yeah. Yeah, it's the mass that matters here. Yeah. Yeah. Okay, so here's it's a set of equations that basically describe massive neutrinos that you need to add to the previous set of long set of equations if you want your neutrinos to be massive. Again, They are all coded up in public Boltzmann codes like CAM and class, so you don't have to do the coding yourself unless you want to learn it. But anyway, this is actually my last slide. There's a lot that we can do with those equations and try to understand what they mean physically. I'm not going to do technical details, but tomorrow what I will do is to tell you a bit about what are the consequences of this description for non-relativistic neutrinos at low redshift and structure formation, in particular neutrino mass constraint, okay? And I'll also talk about relativistic neutrinos that are free streaming or not free streaming around the CMB times and how that can be used as a probe of non-standard neutrino interactions as well as neutrino decay. So I'm going to stop here, and I should leave this with you. Okay, thank you.